Hello, everybody. This is Fisher Yu. I'm an incoming professor at the Computer Vision Lab at ETH. Today, I'm going to talk about tracking, which is one of my favorite subjects in computer vision. So, first of all, what is tracking? Actually, if you look up a dictionary, such as Oxford Dictionary, it gives a very accurate definition. It says that the verb of tracking is to follow the movements of somebody or something. The follow part is actually quite important in computer vision. And in computer vision, something usually means a point, a region, or a template. And somebody can mean an object with known identity. It means a person, a vehicle, or face, those things you have seen before and you want to find and track in a new video. Let's talk about follow first. It's actually an interesting fact that the first film ever is about tracking a horse, and it's actually for scientific purpose. We are always curious about whether in any time the forelegs of the horse are all above the ground, and this tracking of the horse by the first film actually answer that question. And in computer vision, we basically mean the same thing. We want to track our object of interest across the videos. And it basically means that at the object level, it basically means that we have a frame T and we have a target object, or we have a target region, a point, and or just a template. And then we want to find it in the next timestamp or in the future of the video. So after understanding what is follow and what do we want to follow or what can we follow, usually follow can means that we want to track a point, like the tip of the nose of this subject, so that we can find this point in the other frame and find point-wise correspondence. Or we may be interested in a region, and this region can be some primitive, like a rectangle, a ellipse, or a circle, and we may want to know its location in the whole video. And it can also mean a template, like say I give you a rectangle of these two eyes and I want to find it in the future of the frames, or I give you a template of some random pattern so that you can find it in the video and then replace the random pattern with another like object so that we can achieve augmented reality. And it can also mean a part of the object, and the part can have some semantic meaning, like the face of a person, or like limbs or hand of a person, so that we can achieve some applications. For example, by finding the person face, we may be able to identify and understand the motion of a person. And if we can track their hand, then we may be able to create a new interface to interact with computer or some other devices just by looking at the hand gesture. And it can also mean that we can follow the whole object, and the object here can be represented by a bounding box, and we want to find the object in the future frames as a basis for some other purpose. For example, in autonomous driving, we may want to find um, all the vehicles or all the walking pedestrians so that we can avoid them. And it can be a finer granularity than a box. For example, we can track a pose of a person or a pose or key points, connected key points of certain object, so that not only we know their location, their trajectory, we can also know that their behavior, their motion throughout the scene. And it can also mean a segmentation of the whole object. It means that we are interested in some thematic region of the videos, and the thematic region can be, for example, a person, so or a random person in a video, so that we can remove that person from the video and without disturbing the other areas of the images. And why do we want to study tracking? And the primary reason is there are just many and many applications, and it's basically a fundamental building block for perceptual systems or the vision applications. For example, in autonomous driving, we are interested in tracking all the objects and understanding their path trajectory so that we can predict where they can go in the future and then plan our own motion accordingly. And at the same time, we want to react to the action of the other subjects in the scene so that we can achieve safe driving. Or in image editing, and we want to track the like some pattern or some marks or even a general person in the scene so that we can achieve some visual effects. Like in Avatar, this is basically the first ever film that put marks on human face, and so that they can use image processing or computer vision techniques to track the motion of the whole face. And as you can see here, for the whole body, they are using some specialized marker to track the um, motion of the body. But for face, it will be very hard to put all the markers on on every muscle, and then they simplify the setup so that in post processing they can use tracking to find those points and then find the muscle movements. And also in safety monitoring, we can know where the patient, for example, in hospital, we can know that where are the patients and whether there are any nurse taking care of them. Or in sports, that we can understand the motion of every object. For example, if we want to focus our camera on the ball, then we can just track the ball and then uh, take follow follow the motion of the ball to change the camera angle. And if you are interested in AR or VR game, this is a demo from Microsoft. And the reason that they can achieve this realistic blending or mixing of their um, video game and the real scene is the holo is that their device can track the pattern like the wall and then find their 3D projection, find their perspective and transformation parameters so that they can fit their game subjects perfectly into the scene. Or if you are a business like um, um, supermarket, you are interested in where your customers visit in your shop and what will the hotspot, which part of your shop will receive the most attention, then you can use tracking to track the person, and then you will understand that where they go and where they look at. And this can also be used in some other scenario other than watching people. For example, as the video show here, you can also watch cows and see that their behavior and make sure everything is fine, and also understand that whether they are utilizing this space as expected and whether they are raised as expected. And so for some other business purpose, you may want to track the human pose and their action so that you can accurately count the person. And for example, in this case, in the subway station, you'll know that where the people are walking and how many people are using the entrance and how they are interacting with those gates. And there are those are just some samples of applications to use tracking algorithms. And of course, because it's so popular, it has been basically used in every corner of our life. And for example, in a recent live streaming of a football game, it says that the host want to use tracking technology to stream their game so that they can automatically change their camera system so that it can always focus on the action and focus on the ball. And unfortunately, because the efficiency of their tracking system, it was actually very funny to see that the camera keep tracking the head of a judge just because it looks like a big ball, um, and the game watchers cannot really see where the ball goes because the camera keep focusing on the bald head of this set judge. Tracking tasks are usually divided according to several aspects. The first aspect is the shape of the tracking targets. It means that you may want to represent your target in different ways. You may say that I want to track a point, like a corner, so that I can use it to find correspondence across frames. Or you may say that I want to represent my target as a box, so that because you only care about its location and extent. Or you want to have a more finer grained understanding of the target so that you want to know the segmentation or the pixel level information of your tracked objects. A second dimension is what prior knowledge you have about your tracking target. Are you tracking any object target where you only know its appearance or some examples, or you do know some properties about the target? Say you are tracking a corner, or you know that the target is a planar object, even though it's in a 3D space. Or you may already know some semantic information about the target. For example, you can tell me that you are tracking a vehicle, and before I see the real testing video for the tracking task, you may already give me thousands or even millions of examples to show me what is a vehicle. And in general, there are two scenarios for the tracking task. The first scenario is we track without a concrete example. However, you do give some concrete information about the object. For example, we may be tracking a known category such as corners or vehicles. For those objects or for those targets, we may have some image processing properties that we can trace, or we have some models that help us to locate those objects. And this scenario is primarily used in autonomous systems in complicated environments. For example, for self-driving car, or for like 3D reconstruction or 3D mapping to understand the whole 3D information for the scene. A second scenario is you may want to track a specific object, and this is usually happen in image editing or in some interactive systems. In this setup, for example, you give me a video and an example of object you are interested in, and usually this information is given by the segmentation or the target in the first frame of your testing video. And then you tell me that you want to find the same objects or the same target in the rest of the frames in this video. While tracking tasks have so many interesting applications, we also face a lot of challenges in solving those tasks. First of all, the temporal information introduced by the tracking task just adds another dimension of difficulty to image analysis. It elevates our 2D task into 3D, and we always need to worry about how we can use those multi-frames together and how do we represent the shape in our tracking task and represent the association for tracking those shapes. And second, we are having a lot of data when we want to do video analysis. Just consider that a normal video, which is 30 frames per second, and every minute we are generating almost 2,000 frames of images. And you can imagine that we will have millions or even billions of images easily for analysis, and it's especially expensive to run deep learning models on every frame of a video. And also, it's very important to understand how we can incorporate prior information in solving the tracking tasks. In most of the cases, our focus for tracking is how we can associate objects across different frames. However, sometimes even locating the known targets, say finding the people in a video, may become the accuracy bottleneck for the tracking tasks. It's intellectually challenging, and at the same time, it's very satisfactory to solve a challenging task. And tracking is a basic building block for real-world applications, because in real world, every visual data is coming in a video fashion now. We will soon have IoT devices cover every corner of our life, and we will have autonomous driving cars running at every corner of our streets. And the video sources are just coming from everywhere, and we need adequate algorithms to process those videos, understand those temporary information, and provide even stronger basis for future applications. Even if tracking is hard, we can always start attacking a problem from the simple case. Let's first start with tracking an unknown point as our first example. So the task of tracking a point is very easy to describe. I give you a point in one frame, for example, the nose tip of this Mickey Mouse, and then I want to find it in the other frame. And likewise, I may want to give you an arbitrary point in the first frame and track it or find it in the second frame. And after you give me the point, it actually sounds easy to find the point with the same color, so that we can say, okay, if those points have the same color, then they should be the same point, or at least the same point should satisfy this color consistency. And we can express this color consistency in the form on the slide. So it says that if we find the correct displacement h to track this point, then the first point, then the first image of the location displaced by h should have the same color with our target point. And our goal here is we formulate this energy function as based on color consistency, and then we optimize the displacement for this energy so that these two pixels under this H will have the same color. And how we can analyze this energy function? Let's take it step by step. First, we can expand this I0x plus H into two terms. The first term is I0x plus H times I0 prime x, and I0 prime x is a derivative of I0 at the location x. This is basically the first order Taylor expansion, and we can use this Taylor expansion to approximate the energy function. This is not a perfect approximation, but later we will find again and again that this approximation has been widely used in the image analysis, especially in tracking objects and understanding the motion. After we have this tracking, to find the minimum of the energy, then we can take a derivative of the energy by h. So you can see that even though h is two-dimensional object, and its derivative is actually very similar to the one dimension, like a variable polynomial of 1 degree. And if we set the gradient to be 0, which the condition of local maximum or minimum should satisfy, then we can get h value. You can see that it is the value difference of I1 and I0 at the current location divided by the gradient of x. So it's worth noting that this approximation will become um, closer to the true displacement when the displacement is very small. In other words, this approximation will become more accurate um, when the motion is small, or the Taylor expansion will become more accurate when the displacement is small. So the intuition behind this is actually very easy. Let's take an example of this one-dimensional signal. So you can see that we have two continuous curves on I1 and I0, and I1 minus I0 is the difference at this location x between these two curves on one dimension. And the gradient of I0 at the location x says that how we can update h so that we can find the same point on the curve of I0 and I1. However, there are a couple problems with this elegant solution. The first thing is, what if the image gradient is 0? It will lead to dividing zero error for calculating h. And when the gradient is 0, it means that the image region is flat. And it's very easy to understand from a one-dimensional curve. It basically says that you are in a flat region on this curve, and you do not know that where you can match to. And it also means that there are potentially multiple solutions when you try to match this flat region. And this is something called the actual problem. It's actually quite famous. It says that if we want to have well-defined tracking, we need non-zero gradients in all directions. And onto the image, it means that we will have non-zero gradients on both x and y directions. And if any of those gradients are missing or zero, that means we cannot determine the relative motion. And this also lead to the illustration of barbell pole illusion. As you can see, if you are only looking at part of the barbell pole, depends on which area you are looking at. It's actually very hard for the human visual system to decide that where the stripes are moving, as we know that actually the barbell pole is rotating, but if we only look at part of the pattern, we have the illusion that the stripes are moving upwards or moving like in the vertical direction. The second problem is this simple matching may run into local minima. Remembering that when we derive h, we assume that the energy E only have one minima, and that's usually not true for very complex signal. And we all know that the image can be very complicated. And that means that if we take the simple local minima, then when the curve is very complicated, or when the signal has multiple modes, as we shown in the figure B here, it will be very hard for us to find the correct matching. And at the same time, a lot of our assumption in our derivative, in our equation derivation is not correct. And this local minima can be exemplified by repetitive pattern, like those we commonly observe in the checkerboard or in a brick. And in the real world, especially in the modern city, we see sky wrappers around everywhere. And if we use our simple method to track the points, we will easily lose the tracker. So recall that optical flow can be treated as point tracking, even though it's trying to recover the motion everywhere. And one key assumption for the optical solution is we recover smooth motion. And this leads to least square regulation, which is a horn shrunk makes a smooth spatial change assumption. In that formalization, we add additional regularization terms in our solution so that we can solve the motion at every point. The assumption or regularization assumes that the locally all the points will move in the same direction. And recall that in optical flow, we have this equation, and it's a relation between the image derivative across x, y, and the time with the displacement at a particular pixel x and y. And for each of these equations, we can get a relation of these two unknowns. And remembering that when we derive this equation, we assume that displacements u and v are small, and we can use Taylor expansion to approximate the solution. And in tracking, we can treating the actual problem in the same way. We can get additional information to constrain the motion. So in optical flow, we assume that everything moves smoothly in the space, and in tracking, we can assume that for a small region, they all undergo the single motion. For example, the small region can be a patch, a very small patch like 5 by 5 in your high resolution image. And all this, every pixel in this region will conform to the spatial coherence constraint that pixels neighbors will all move together. The illustration on this slide shows an example for 1D signal. Each pixel will give us one constraint for this two-dimensional displacement u and v, and for n points we will get n constraints. It's an overdetermined system of equations, and we can solve it by taking the pseudo inverse of the matrix, and here is a 2 by n matrix, and when we multiply this A transpose times A, we can actually get a 2 by 2 matrix. And on the other hand, when we times A transpose with B, which B here is the derivative along time, then we can get another vector which is 2 by 1 dimension. So you can see here, now we have another linear system which is nicely constrained with two variables. And for this system, u and v can only be found if the matrix is invertible. And also, we say that the solution is stable if the 2 by 2 matrix has no small eigenvalue. Otherwise, when we calculate u and v, the condition number of the matrix will be very big, which means that any perturbation to the matrix may lead to big change in u and v. And this matrix and the requirement may sound familiar to you, so where have we seen them? Recall that this is exactly how we look for Harris corner detector, and therefore, when we want to find the good features for tracking, this is exactly the same for finding reliable image features. And you may have seen this figure. So lambda 2 and lambda 1 are the two eigenvalues of this 2 by 2 matrix in our linear system. And if both of the eigenvalues are 0, it means that even if you are looking at a bigger region, looking at the neighbors of the pixel, they are still in a flat region, and we still cannot determine the motion of that pixel together with these neighbors. And in this case, we may need to consider even bigger range of neighbors, like grow from 3x3 patch to a 5x5 patch in order to determine the motion of the pixel in the middle. And if one eigenvalue is significantly bigger than the other, it means that we are in an edge area. So in terms of tracking, it means that we can only determine the motion along one direction, which is the perpendicular to the edge direction. And for the direction along the edge, we cannot decide the motion. And if we want to fully decide the motion on these two directions, we have to go into the corner area, which means that the 2x2 matrix for the linear system is well constrained, and it has almost a similar eigenvalue. If the two eigenvalues are exactly the same, it means that we are in a circle area, and those areas are very easy to track and very easy to locate. Here is a classical example for those cases. The red box shows an example of a flat area, and you can see that that is the scan area. And even if we look at so the surrounding of the red box, they look very similar. And if the video change in that area, it's very hard to determine the moving direction of those pixels. On the other hand, if you look at the green box, it's an edge area, and we can easily decide that perpendicular to the ridge of the house or the ridge of the building, ridge of the roof, how the pixels are moving. But along the ridge, it will be very hard to decide the motion direction. And if we look at the blue box, is so there are a lot of small blob or circle-like shapes, and you can see that if the motion or if the video change the location a little bit, we can easily relocate those shapes or relocate this almost random pattern, so that we can easily constrain the motion in x and y directions. And this is an example of the tracker, KLT tracker used in real video. As you can see here, this video has a very small motion. I actually took this video by myself, and the motion you observe is the motion that I try to hold the camera still, but still there was some shaking of my hand. And in this case, because the motion is very small, I can easily use the formula I just described to track the corner areas in this image and find the correct correspondence. And with those correspondence, surprisingly, we can find the 3D structure of the objects in the image. As you can see here, we can reconstruct the small vehicle in 3D space with a very small motion. In summary, when we want to track a point, we had better consider its neighbors to avoid the actual problem as much as possible. And even so, we may not be able to decide the point motion in certain directions, depends on whether the motion fall on a flat region or on an edge. And what if we want to track a bigger area instead of just one point? And this problem comes up when we want to track a template image, and we will have to compare it at each frame. So the previous methods typically applied for some small patches, like say 5x5. And why can we run it on an entire object when we have a much bigger window? And for example, instead of only consider a patch of 3x3, 5x5, or 7x7, we want to consider that we want to track this vehicle across the video, and the target bounding box is 80 by 50. And when we consider a bigger patch, so some other factor come into consideration, especially what if the templates take some transformation across the frames? And of course, we want to be invariant to translation, which means that even if the objects move in the 2D space, we can always find it. But what if the object is rotated, scale, or even take some projective transformation? And how we can compensate those effects when we match the frames? Of course, when the image patch or when the object is rotated, scaled, or have some deformation, other type of deformation, just comparing the pixel value won't give us very satisfactory results. And we can extend our pixel tracker into a template, and this is called Lucas Canadi template tracker. And we can easily generalize the motion model to a parameter space. Remember that when we want to track the pixels, we are looking for a displacement in x and y, so that after compensated by the displacement, the image and target, the source image and target image will look the same in the sense of this L2 distance. And build on this idea, we can consider a parameter P for the warping, so that after the warp of the first image, or the warp of the source image, it can look exactly the same with our target image. And this warping can represent a wide range of parameter space, and it's a general case for translation, where the warping is just the addition of x plus its parameters. First of all, we assume we know the optimal warping or the exact warping from source to the target image. And in the original formulation, the translation of the pixels is a special case for the warping, and the warping can also be scaling, rotation, or some other perspective change. And in the original setup, this square is the difference between the warped source image and the target image, and it's still the same in our new setup. The only difference is instead of updating the coordinates, now we are updating the warping parameters. And now let's see what we can get with this new formulation. First of all, we can still take the use our old trick, take the first order Taylor expansion to linearize the equation or linearize the warping of the first image. Then we can get a new least square problem. And as you can see here in the brackets, there are three terms. The first term is the warped image based on the current parameter, and the second term is the gradient times the change of the parameters, and then the third term is the target target image. At the second step, we can just take a derivative of the change of the parameters. And if you take a closer look at the Taylor expansion, it's literally it's actually a linear equation of delta p within the bracket, and therefore we can actually very easy to take a derivative of delta p of this whole energy function. And we can use our old trick. We set derivative to be 0, and now is actually a multi-dimensional equation. And when we set this the whole vector to be 0, and then just similar to the one-dimensional case, we can easily resolve the value for the change of the parameter. And this equation looks slightly more complicated than the one-dimensional case, but you should not be scared by it. It basically says that we should update our parameters based on the difference of the images and adjust it by the direction of our gradient. And H here is the Hessian matrix. And you can see it's actually very similar to a Newton update. The only complication here is everything is in a in a high dimension in a multiple dimensional space, and a lot of our metrics in consideration here is in it has multiple elements. So based on this formulation, we can have the exact step for our template tracker. First, we have an initial warping parameter P, or it can be the identical parameter which represents the current state of the source image, or you may estimate it from some other source. So after we warp the image based on the current parameter P, and then we can calculate the error image, or the difference between the target image and the current warped image. And then we can warp the gradient of this image with the current warping. So the first step would be to evaluate the gradient of the parameter of the warping at the current location. And then we can evaluate the combination of the image gradient with the warping gradient. It's also the steepest descent images. And we can the next step is to calculate the Hessian images based on the steepest descent images. So putting everything together, we can compute the update of P and get a new parameter space for the warping. And we will iterate the whole computation again and again until the change of the parameter become very small. And this whole process and its variance has been well documented in the framework called in a paper published in 2004. So here is an illustration of this process. We can see that it's still the first step is given a template or target image. We will warp the source image. The source image can be like a complete image, in which we want to find the target template, and then we can give an initial estimation or current parameter space. The step 1 is to warp the image, and then the step 2 is to take a difference between the warped image and the template to calculate the error. And after we get the error, so the second step will be we can calculate the gradient image, and the gradient image will look like more or less like this. So it's very similar to the gradient image we use to detect corners or detect edges in image processing. So the first step would be to calculate Gaussians like this, and then combine them with the warp image. Well, by the way, the Jacobian the derivative of the parameter. This is the derivative of the parameter space, or we also call them the Jacobian matrix. And then we combine them together to get the steepest descent images. And then we use them to calculate the Hessian matrix and also update the parameter space based on this. When we combine them together, we can get the update of the parameters and then come back to our combine it with our current parameters to finish one update or one loop for the parameter adjustment, and then we keep running the loop. So there are several good things about the framework. First of all, it's a very beautiful framework, and it can handle different parameter space. And in a high frame rate video, it usually converges very fast because we only need to take several iterations of updates. And there are also some drawbacks, is it may not be robust to image noise. It's assuming that we have a perfect model for the warping, and it may not be very robust to large displacement when where the image can still get stuck into a local minima. And another problem is the assumption of known parameter warping parameters. Some transformations will be impossible to parameterize. For example, if we want to track a 3D object instead of a planar image, we know that if it's rotated in 3D, it will be very, without knowing the 3D structure, it will be impossible or at least very hard to uh, to warp one transformation to the other with only the knowledge on 2D. In summary, after we learn how to track a point, we can easily extend the same methods to tracking a bigger area template, which represent a bigger box and which will be affected by the image transformation. And we can consider the transformation in our model, and so that instead of adjusting the motion or displacement of the points, we will adjust the warping parameters.